Okay, now we're going to take a look at the mean value theorem. So the mean value theorem says, suppose f mapping the closed and bounded interval AB to R is continuous on the closed interval and differentiable on the open interval. Then there exists some C in the open interval AB such that f prime of C is equal to f of B minus f of A over B minus A. So this right-hand expression is the average rate of change of my function on the interval AB. So average rate of change of f on AB. And then we know that the value of the derivative is the instantaneous rate of change of f at C. So this theorem is telling us that when you have the right conditions, so continuous on the closed interval and differentiable on the open interval, then that means that there has to be a point in your interval AB where the instantaneous rate of change of f at that point is actually equal to the average rate of change over the whole interval. So taking a look at a picture of what this means geometrically, so suppose I just have some function. Here is my interval I'm working over. So here's A, here's B. I've got f of A and f of B. So the average rate of change is computing the slope between the points, the end points essentially, of my interval. And so I get something like this. So I'll go ahead and extend this a little further on this side. So this is a secant line, and the slope is the average rate of change, f of B minus f of A over B minus A. And we know that instantaneous rate of change can be computed using the slope of the tangent line at the point you're looking at. And so this is claiming that if I take a look, I can just duplicate this line and move it parallel. There should be a place where that parallel line hits the graph locally at one point, and that's your tangent line that has the same slope as the average rate of change, and this happens at some point C. And so here, this is the slope of the tangent line at C. Now, if you notice, there's another spot on this interval that my slope of my graph is also the average rate of change over the interval, say right here. The MVT is just saying that there's at least one point. It doesn't tell you how many locations. So there could be more than one value where this is satisfied. All right, so to prove this, notice that this is making a claim about the derivative equaling a specific value. And we just got done proving the interior extremum theorem, which is a theorem that tells us conditions that would be enough for getting the derivative to be equal to 0. This suggests that if I was in the special case where f of b minus f of a over b minus a was equal to 0, then perhaps I might try to use the conditions of the mean value theorem to show that the conditions of the interior extremum theorem are satisfied, and then I could just apply it. So we're going to start with a special case. Proof. So here's our special case. And once we understand how the special case works, then we're going to generalize it. So the special case where f of a equals f of b. If that happens, then the average rate of change over my interval has to be 0, since f of a equals f of b. Now, many of us know this theorem already, and we know it under the name of Rolle's theorem. So in this case, if I look at f of a minus f of b over b minus a, that will have to be 0. So my goal is to find a location of a point C where I can guarantee that f prime of c equals 0. And the IET says I can do that if I have a C value where I achieve a local min or a local max. So this begs the question, how am I going to argue that I can find such a point? So the first thing is I need to explain why should I even expect my function to have extreme values? Well, this is why it's essential that f is continuous on the closed and bounded interval AB. We needed it to also be continuous at the endpoints, because when we have that, that implies that f is continuous on a compact set. So by the extreme value theorem, which I'll abbreviate EVT, f achieves a max and a min on the interval AB. Now, remember, we want to use the IET. If we want to use the IET, it is the interior extremum theorem. And so in order for me to use it, I would need to know that I have an extreme value happening on the interior of my interval. So that sort of begs the question, what happens if both the max and the min are not occurring on the interior? So what that really means is that the min occurs at one point and the max, one endpoint of the interval, and the max occurs at the other. So we need to explore that case. So case 1. F achieves its max and min at the endpoints. Well, if that's telling us that because f of a equals f of b, that says that the max is equal to the min. And the only type of function where the max is equal to the minimum value is a constant function. Because the moment f takes on two different values, there's no way that the min and the max can be the same. So, because f of A equals f of B, f must be constant. Well, if you're constant, then the derivative of your function has to be 0 over the entire interval. So this says that f prime of C has to be equal to 0, which is indeed f of B minus f of A over B minus A, and this is true for all C in my interval. In fact, it's true at the endpoints as well, but all I needed to do was find one location where I could guarantee that that f prime of C on the interior was equal to 0, and I've done that. So otherwise, I need to consider the other case. So assume that f achieves an extreme value at some at some C on the interior. So we did the case where both of the extreme values were at an endpoint. So now we're sort of saying, well, assume at least one of them is not at the endpoint, it's on the inside somewhere. Well, then we can just straight up apply the IET to say that f prime of C has to equal 0 because it is a local max or a local minimum value. In fact, it's global, which any global max also has to be a local min or a local max. So in either case, we have shown that in the special case that f of A equals f of B, we can always find a point C where the derivative is equal to 0. The general case is just going to be us adapting this argument so that we can get the derivative equal to some non-zero value. And the way we do that, if I want to show that the derivative, if I know how to show that the derivative of a function is equal to 0 somewhere, then what I can do, if I want to show the derivative of a function is equal to something non-zero, is show that the derivative of some shifted function is 0, such that when you solve that shifted function, it's equivalent to the equation f prime of C equals some non-zero value. So what we're going to do here is we are going to apply case 1. So we're going to apply Rolle's theorem, our special case. To the following function. Capital F of x equals little f of x minus f of b minus f of a over b minus a times x minus a plus f of a. So you might be wondering why this function and how on earth would you think to do this? So why does this make sense? So we want to show that f prime of C equals f of b minus f of a over b minus a. And we know how to show that a function, some other function, f prime of C is equal to 0 somewhere. So what we're going to do is choose capital F such that f prime of C equaling 0 is equivalent to little f prime of C being equal to f of b minus f of a over b minus a. So we just need to see that f prime of c has the right formula such that it being equal to 0 is enough for us to rearrange and get the result we want for the mean value theorem. So notice that the definition of our function that I've selected up here is such that if I plug in f prime of c, I'm going to get little f prime of c minus, now this is just this part is just a line, and so its slope is exactly its derivative. And so certainly if that is equal to 0, then all I have to do is take that average rate expression to the other side, and I have what I'm looking for. So we're going to refer to this line that we gave slope f of b minus f of a over b minus a. We're going to call it g of x. Let's just take a look graphically at what's happening here, because if I'm really going to apply Rolle's theorem to my big F function, then I need to make sure I can actually show that its hypotheses are satisfied for big F, and that depends on understanding sort of what the graph of this function looks like and why I chose this particular equation of a line in order to subtract that from f of x. So if I take a look at my function, let's just draw something simple. So maybe I have something like this. If I go ahead and I draw my secant line that goes through f of a and f of b, then notice that the equation of its line is exactly y equals g of x. And then the equation of this curve here is y equals f of x, little f of x. And so all big F of x is doing is it is subtracting the two. It's saying take little f of x minus g of x. And so we need to check that the hypotheses of Rolle's theorem are satisfied for capital F. So then I can just apply it. So check hypotheses of Rolle's theorem are satisfied on the interval AB. So first of all, that means I need to check that capital F is continuous on this interval. Well, capital F is continuous on this interval. Because it is the difference of continuous functions. Little f is known to be continuous, and then the other one's just a line. So I'm applying the algebraic continuity theorem here. To get differentiable, it is just an application of the algebraic differentiability theorem. If I take a look at what f prime of x is, it's just little f prime of x minus g prime of x. This has to be, we know this exists. We know that capital F is differentiable by the algebraic differentiability theorem because f and g are differentiable. And then the last thing we have to check is that capital F of A is actually equal to capital F of B. And in order to do this, I just take a look and I see that, hey, at the endpoints on my graph, little f and little g are equal. So f of A, little f of A equals g of A. So I'm going to write that over here. Little f of A equals g of A, because my graph is intersecting there. And I also know that little f of B is equal to g of B. So that tells me that big F of A has to be 0, because I'm taking the difference of those two values. And same thing for big F of B. So I am in the special case of Rolle's theorem. So by Rolle's, I can say there exists some C in the open interval such that big F prime of C is equal to 0. But what that means is that big F prime of C, which we know is going to be little f prime of C minus f of B minus f of A over B minus A equals 0. And that implies rearranging that I have found a place where the instantaneous rate of change is equal to the average rate of change over my interval. So when we come back to class tomorrow, we will take a look at some of the results that we get that are familiar to us from calculus, things that we use for analyzing sort of maybe the graph of a function or behavior of a function. Just all of these are going to follow from knowing that the mean value theorem is true. See you tomorrow.